Hello, my name is Daniel DeFelippis. I am a graduate student at Columbia University, and I will be talking about my most recent paper where I study the circumgalactic medium, or CGM, of galaxies in the TNG50 simulation and compare them to a subset of magnesium-2 observations of the CGM called the MEGAFLOW survey. So this particular subset of MEGAFLOW observations has sightlines that pass near the major axis of their associated galaxies and probe magnesium-2 gas that, as shown by this plot, is rotating in the same direction as the galaxy. So my previous work on angular momentum and rotation in the CGM using illustrious and illustrious TNG therefore motivates me to see if the kinematics of this observed gas are also found in this high-resolution cosmological simulation. So to do this, I used a tool developed by Cameron Hummels called Trident, which post-processes galaxy simulation outputs to generate absorption line profiles using mock sightlines. So this process is demonstrated here, where I show magnesium-2 column density maps of a simulated halo along with a sightline through that halo going left to right that passes near the galaxy's major axis. So each gas cell that intersects with the sightline is colored by its velocity along the sightline and is used by Trident to make this resulting absorption spectrum. So in this particular example, the gas along the sightline is clearly co-rotating with the galaxy at velocities that are near the virial velocity of the halo. So now that I've demonstrated the main analysis technique, let's take a look at some results. So first, showing some individual observed spectra in blue, along with individual spectra from TNG50 in orange, chosen from this halo mass range at redshift of 1 in order to mimic the properties of MEGAFLOW. So what should be clear is that individual TNG50 halos reproduce magnesium-2 spectra of individual MEGAFLOW systems very well, despite the diversity that's present in the observations. So next, I'm showing a stacked spectrum from both TNG, this time red, and MEGAFLOW in green, which demonstrates that the agreement between the spectra on the previous slide isn't unusual, right? So in other words, the average spectra of MEGAFLOW-like systems in the simulation are also similar to real stacked spectra, right? They're both symmetric. Both have similar absorption depths. They're both centered at about half the virial velocity or so, and they both show a clear preference for co-rotation. So I'll note here that in our paper, we look in more detail at the spectra's dependencies on things like radius in the CGM and mass of the halo. So this next result comes from analyzing the full 3D kinematic information of the magnesium-2 gas in TNG50. So these are mean radial velocity profiles of magnesium-2 gas in black, and then cold and hot gas in the halo in blue and red, respectively. So if you focus just on the bottom left of the plot, where the arrow is, you can see that the magnesium-2 and cold gas in general both have net inflowing velocities of about 50 kilometers per second in the inner regions of the CGM out to about 40 kiloparsecs or so. And in particular, the strongest inflowing velocities occur where the azimuthal angle alpha is less than 45 degrees. So this, or in other words, where the gas is closest to the major axis, which is exactly the same gas that has strong co-rotation. Finally, I'll show this plot of the angular momentum of different components of the halo as a function of galactic stellar mass. So if we just focus on the magnesium-2 line in black, the median, what's clear here is that the angular momentum of circumgalactic magnesium-2 by itself matches that of the rest of the CGM, the cold part and the hot component, very, very well for over 2 orders of magnitude in galaxy stellar mass, right? 10 to the 9 to 10 to the 11 solar masses. So this, I think, indicates that magnesium-2 can be a very powerful tool in calculating fundamental kinematic properties of the CGM. So I will finish now by leaving my conclusions up here. Please check out the paper using at the link displayed on the bottom if you're interested in learning more. I hope you enjoyed the video, and thanks for watching.